Today, we are zeroing in on a really crucial aspect of AI. So, how do we actually know if these intelligence systems are performing well, especially when they're pulling information from all over to answer your question? So we are deep diving into evaluating AI agents that use something called Retrieval Augmented Generation, or RAG. Think of it as ensuring your super smart AI assistant isn't just finding random stuff online, but is actually grabbing the right information from database, PDF, knowledge base, or whatever, and using it accurately. So our focus today is going to be on a really good tool called RAGAS. So in a world run by AI, you really want to be sure that you can trust the information it provides. So this video is going to give you a real understanding on how developers are working behind the scenes to measure and improve the reliability of these AI agents. It's about making them not just smart, but also dependable. And it really comes down to this idea of metric agent development. So instead of just sort of guessing if an AI is getting better, we use measurable results, hard numbers. Okay, so let's get into the specifics of RAGAS setup I'm going to show you today. So we are going to use an AI large language model from OpenAI called GPT-4o, and we are going to use a framework called LangChain to kind of manage everything. And the key part of this is what we call the search tool. Think of it as an AI librarian almost. It's responsible for finding the right books, or in this case, data in a massive archive. So when you ask the AI question, the search tool kicks in first, takes your questions, turns it into something like a digital fingerprint using an embedding model. That fingerprint or embedding then goes to a special kind of a database called vector database. Now, instead of just searching for keywords, vector database looks for these digital fingerprints that are likely semantically similar to your question. And why is that so useful compared to just keywords? Well, think of vector database as this specialized library just for these numerical representations, these vectors. Instead of just sifting through every single document individually, it can quickly identify documents with similar meaning based on their vectors. It makes the search process much faster and more efficient, especially for large data sets like finding books on similar topics, even if they don't use exact same words in title. So in this example, VectorDB retrieved, say, 3 of the most relevant pieces of information context. These are then passed back to the search tool and then onto the actual agent, in this case GPT-4 agent. So the agent then takes those relevant snippets, those contexts along with your original question, and uses all of that to construct its answer. Okay. So just to be crystal clear for everyone watching, that search tool part finding and retrieving the information, that is the R in RAG word. And the GPT-4 agent taking that information and actually writing the answer, that's the G in generation. And that is where RAGAS come in, to evaluate both parts. RAGAS steps in to give us a much more detailed picture of how well both of these parts are working. The RAGAS doesn't just give you a vague feeling like good or bad. It provides specific metrics. Think of them as scores to evaluate both the retrieval, the R, and the quality of the answer that generated the G. This allows for a much more precise understanding of, where improvements can actually be made in the system. Right now, in order to evaluate how well the AI is retrieving the information, you actually need to be able to see what information it pulled in the first place, which makes sense. Apparently, when you're setting up agent using LangChain, there's like a little switch you need to flip, a parameter called intermediate steps that you just set to true. This makes sure you can see those crucial intermediate steps, including the retrieved context, which RAGAS then analyzes. Yeah, and what's fascinating here is how this simple configuration, just setting that flag, unlocks a much deeper level of understanding, because without seeing the retrieved context, you could only really judge the final answer. But by capturing these intermediate steps, RAGAS can tell you not just if the final answer is good, but also if the AI even pulled the right information to begin with. It's kind of like being able to see the notes of a student took before they wrote an essay, not just essay itself. Okay, so once you've got that set up, RAGAS needs the data in a specific format to do its evaluation. We are talking about needing the original question that was asked and what's considered the absolute best, most relevant information in your data set for answering that question. That is called ground truth context. So ground truth context and then the ideal answer you hope the AI would give, that is referred as the ground truth answer. So think of it like having an answer key for the whole process. You've got the perfect answer, you've got the perfect source material that leads to that answer. This ground truth data allows RAGAS to compare the AI agent's actual performance against this known benchmark of excellence. So the idea is taking a bunch of questions, feeding them into your AI agent, and then keeping the track of the information the agent used, the context, the answer it came up with, and that all-important ground truth information, and then we set how many questions we want to test. And after we run these questions through the agent, we end up like a structured table of information called data frame. This table neatly lays out the original question, the AI's generated answer, the specific context used to generate that answer, and the ideal ground truth answer. With all of these pieces lined up, RAGAS can now jump in and apply this evaluation metrics. And this is really where the magic happens. You could say we move from simply having an AI that answers questions to actually understanding how effectively it's doing so quantifiably. RAGAS takes this structured data and applies its set of evaluation metrics to give you these scores, these numbers, about the quality of both stages in retrieval generation. Alright, let's dive into these retrieval metrics first. The ones telling us how well the AI is finding the right needles in the information haystack are called context recall. You might also hear it as a recall at K. So what does context recall tell us is at its core, it measures how much of the actually relevant information that exists within your entire data set was successfully retrieved or pulled out by our pipeline. So it's really about making sure the system doesn't miss any crucial piece of the puzzle, and the calculation formula is true positives divided by true positives plus false negatives. In simple terms, true positive is when the system correctly finds and returns relevant information. That's good. So what's a false negative in this context? False negative is basically a missed opportunity. It's when there was a relevant information sitting there in your data set, but the retrieval system, for whatever reason, failed to find it and pull it out. It missed it. So context recall essentially tells you what percentage of all the important stuff your system managed to grab. One of the interesting things is that the recall at K defaults to K5. So what does that mean? So K refers to the top K number of documents that the retrieval system is allowed to return or consider. So if K is set to 5, we're looking at whether the relevant information was present within the top 5 documents retrieved. But increasing K to say 10 or 20 means the system looks at more documents. This can help recall because you're casting a wider net. You might catch more relevant things, but it becomes less practical for actually filtering down the information the agent will ultimately use. Imagine asking for the top 5 most relevant paragraphs versus the top 100. The agent has a lot more potentially irrelevant stuff to sift through in that later case. You could set K to be incredibly high and probably retrieve almost everything relevant eventually, but you'd also be pulling in a ton of irrelevant junk, which isn't helpful for generating concise answer. Now, the second retrieval metric is context precision. This acts as a sort of a counterweight to recall. So how does it work? What's the difference? So the context precision shifts the focus a bit. Instead of asking, did we find all the relevant documents? Precision asks of the documents we did retrieve, how many were actually relevant. It measures the proportion of the returned documents that were genuinely useful and on topic for the original question. And the formula reflects that. It's true positives divided by true positives plus false positives. So it's comparing the number of good results returned to the total number of results returned, both the good ones and the irrelevant ones. And this is why it's a counterbalance. Unlike recall, simply increasing K, allowing the system to return more documents, won't automatically improve precision. Because while you might capture more true positives by increasing the K, you'll likely also pull in more false positives, more irrelevant stuff, which would actually lower your precision score. So a high context precision score tells you that when your system retrieves documents, a large percentage of them are actually useful and on topic. Those are the metrics for judging how well the AI is finding the right information retrieval. Now, let's turn our attention to evaluating the generated answers themselves, the G part. The G part tends to be a bit more about quality and content, more qualitative perhaps, and often assessed using LLMs themselves. So evaluating the nuance of generated text is tricky, and what can we do? The first thing we can do is measure the faithfulness. What does faithfulness score tells us about the AI's answer? So faithfulness is all about factual accuracy and consistency with the source material. It measures the degree to which the claim made in generated answer are actually supported by the information in the retrieved context. So a perfect score of 1 means every single statement, every claim in the answer can be directly verified by looking at the context the AI was given. A score of 0 means, well, none of the claims are supported by the context, which means the AI might be making things up or going off script. And how are we calculating this faithfulness score? The calculation typically involves another language model, an evaluation LLM. This evaluator LLM looks at the answer generated by the agent. It breaks it down into individual claims or statements, little facts asserted in the answer. Then it checks each of these claims against the retrieved context to see if there's evidence there to back it up. The faithfulness score is then essentially the number of claims supported by the context divided by the total number of claims made in the answer. Basically, it's asking, did the AI stick to the facts it was given or did it hallucinate? But even if an AI retrieves perfectly relevant information like their recall score suggested, it doesn't automatically mean it will use the information correctly or truthfully in its answers. The retrieval can be perfect, but the generation fails. So if we have low faithfulness scores, that could indicate that the AI is hallucinating, making stuff up, or maybe misinterpreting the context, even when it had access to the correct information. It's a crucial metric for identifying potential inaccuracies or, well, falsehoods in generated output. And it's really good indicator of where you might need to dig deeper and see why the AI went off track. So the second generation metric is answer relevancy. This one seems pretty straightforward. It's about how raw the generated answer actually addresses the original question. Answer relevancy gets to the heart of whether the AI actually answered what you asked. Did it stay on the topic? Again, it relies on an LLM, but in a really clever way. We use another language model to generate multiple follow-up questions based purely on AI's generated answer. The idea is if the answer is focused and directly relevant to the original question, then the question an LLM could plausibly generate from that answer will likely be very similar in meaning to the original question you asked in the first place. Here, we can use a technique called cosine similarity, which is just a mathematical way to measure how similar two pieces of text are, meaning comparing these LLMs generated questions to the original one. High similarity score means high answer relevancy. So if the AI answer wanders off topic or includes a lot of irrelevant stuff, the follow-up questions you could generate from that rambling answer would probably be quite different from the original specific question you asked, lowering that score. All of these different metrics give you a multifaceted view, and you need them all. An answer can be relevant but unfaithful, or faithful but maybe not quite hit the mark of relevancy. And that is really key takeaway, that these metrics aren't just giving you a single grade like an A or B, they're more likely the different lenses, different perspectives to evaluate the AI strengths and weaknesses. You might have an AI that's great at answering the question, high relevancy, but sometimes makes up facts, low faithfulness, or one that sticks strictly to the source material, high faithfulness, but doesn't fully address the user score need. This detailed evaluation in RAGAS allows for much more targeted improvements to the underlying system. Basically, it will tell you where to focus. And that brings us right back full circle to the core benefit of using a metric-driven approach with tools like RAGAS. By having these quantifiable measures, these scores for both the information retrieval and the answer generation stages, we can iterate much faster and more reliably. It's not a guesswork. We can make a change to the system, maybe tweak the embedding model, adjust the prompt, change the LLM. Then we can run the evaluations again, see exactly how those changes impacted the different metrics, recall precision, faithfulness, and then we can make data-based decisions to build more effective and crucially more trustworthy AI agents. And before you leave, let's take a look at one simple example of a RAG implementation with GPT-4o, LangChain, ChromaDB, and RAGAS. Okay, we're gonna use a Jupyter notebook and LangChain example today. First, we need to install our dependencies. We're gonna install the LangChain, the OpenAI integration, ChromaDB vector database, and the dataset library for our knowledge source and evaluation data, and of course, RAGAS. First, we're going to need an open API key for our embeddings and agent LLM. And this cell here securely prompts you, and then it saves that API key as an environment variable. Then our agent needs knowledge to draw from. We're loading a pre-chunked data set of AI research papers from ArXiv, and they are hosted on Hugging Face datasets. We're just loading a subset here for speed. and each item contains a text chunk and useful metadata. So to make this text searchable, we need embeddings. We're initializing OpenAI's text embedding tree small model. It's efficient and really effective. Next, the vector store. We're using ChromaDB because it's open source. So we're going to initialize it here. We're going to point to a local directory, and we're going to persist our data. We're also going to give the collection a name. Now we populate ChromaDB, we loop through our ArXiv data in batches, we extract the text chunks and metadata, then we use LangChain's Chroma integration, add text method, which actually automatically handles embedding and texts using our OpenAI embedder, and then it stores everything we need with its unique ID. Then we persist the changes. Now our agent needs a way to access this knowledge. We define a LangChain tool called ArXiv search. When the agent needs info about the AI topics, it will call this function. Inside, it performs a similarity search directly on our ChromaDB vector store using user's query. So we can test this tool directly and get the result. It takes a query and returns relevant text chunks from our database. Now we'll use a LangChain XML agent structure. We are pairing it with an OpenAI model, and we pull a standard conversational prompt for this agent from LangChain Hub. Then we initialize our OpenAI chat model. Then we set a low temperature to get more factual responses. We also have this helper function to format the tool list and the agent's internal steps into the XML format the prompts expects. Then using LangChain expression language, LCEL, we define the agent's flow: input processing, adding tool info, calling the LLM, and then parsing the XML output. We then wrap this in an agent executor, providing our tools and, importantly, adding conversation buffer memory for chat history and ensuring we return intermediate steps, which is crucial for RAGAS. And now let's chat with the agent. We ask about Llama 2. The agent uses its ArXiv search tool, queries ChromaDB, gets context, and generates the answer. Because we added memory, we can ask follow-up questions like, was any red teaming done? And it understands the context. Okay, the agent works well, but how well? So now it's time for RAGAS. RAGAS needs the question, the final answer, the retrieved context, and the ground truth answer for comparison. We can get these contexts from those intermediate steps we told the agent executor to return. We load a pre-built evaluation dataset containing questions and corresponding ground truth answers based on the ArXiv paper. Now we loop through some questions from this evaluation set. For each one, we run our agent, collect its generated answer, and extract the context it retrieved using the search tool. We store everything: questions, answers, context, and ground truth in a pandas data frame. We convert our results data frame into Hugging Face dataset, the format RAGAS expects. We define RAGAS metrics we care about: faithfulness, answer relevancy, context precision, recall, correctness, and similarity. And now we run RAGAS evaluate. RAGAS uses LLM, defaulting to our configure OpenAI model, to score the agent's performance on each metric for every question. And let's look at the results. Context precision and context recall tell us about retrieval quality. Did we get relevant chunks without noise? Faithfulness, check if the answer sticks to the retrieved context. Answer relevancy, similarity, and correctness. Compare the generated answer to the question and the ground truth. High scores are generally better. So there you have it. We've successfully set up and evaluated a LangChain RAG agent using ChromaDB for local vector storage and OpenAI models for embedding and generation, all assessed using the RAGAS framework. This gives us concrete metrics to understand and improve our RAG pipeline. You can find this link in the description below. If it was helpful, please like and subscribe. Thanks for watching and happy building.